Hello, I'm Jim Burnett of NASA's Lewis Research Center in Cleveland, Ohio. In this 7th program of our series, we'll see a film called Your Share in Space, which was first released in 1962.
We've come a long way in the few years since our country began its broad, long-range program of space exploration. Since 1958, when NASA, the National Aeronautics and Space Administration, was established, we've successfully launched scores of spacecraft. Today, it's no longer a question of what can we do in space, but what we want to do. And for many people, the biggest question of all is, why do we want to explore space? What are we getting for the millions we've already spent? And what can we expect from the billions we plan to spend? Much of this questioning of the practical value of space exploration stems from the fact that most of our space activities are primarily concerned with gathering scientific information which often appears meaningless to the layman and seems to have little immediate practical value. The S-15, our gamma-ray astronomy satellite, is a good example of this kind of space experiment. This satellite, while it looks like an old-time street lamp, is actually a miniature observatory equipped with a powerful telescope to detect high-energy gamma rays from cosmic sources. Gamma radiation, which is produced by nuclear activity, has a special interest for scientists because they think it can be the key to valuable new information about the forces and elements that make up the universe. It was the investigation of phenomena such as this in the past that led to the development of electricity, radio, and more recently, nuclear energy. To simplify and reduce the cost of launching experiments such as these, we recently developed the Scout. This 4-stage launch vehicle is powered by solid propellants and gives us a small but highly flexible booster that we can use for a variety of space probes and actual missions. Apart from contributing to our general knowledge about the Earth and the universe around it, our scientific space experiments also give us the special knowledge and experience we must have to use space to improve our life on Earth, which is one of the primary objectives of our space program. In this area of practical applications, we've already made several spectacular achievements. One of these was Echo 1, a communications satellite experiment using a huge inflatable sphere to serve as a reflector for radio signals. The experiment called for the payload to be placed in a 1,000-mile Earth orbit. Here it would be separated from the 3rd stage, and the sphere would be ejected and inflated. Radar tracking stations would observe and plot its course. Skirting the coast of South America, the satellite orbit would extend below the tip of Africa. And coming back over the South Pacific, it would cross between Australia and Asia, proceeding in a northeasterly direction above Wake, Midway, and Hawaii, and down from the North Pacific within range of the NASA Jet Propulsion Laboratories tracking station at Goldstone, California. This station was to be one of the communications points. The Bell Telephone Laboratories at Homedale, New Jersey, was to be the other. When the sphere reached an area of mutual visibility between these 2 points, they would attempt to communicate with each other by bouncing their signals off the satellite. Our first test in the summer of 1960 failed. But several months later, a second attempt was made.
On. Accelerator. On. Start tank. On. Burn your fuel vent. On. Minus 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 1. tracking normally. Trajectory standard. Main stage cutoff. Ignition stage 2. Antigua has acquired.
Azimuth within limits. Guidance corrected 1/2 degree in elevation.
Trinidad has acquired.
Some 15 minutes after takeoff, Trinidad observed the inflation of the sphere. "35 minutes after takeoff, data from Cape Canaveral indicated that orbit had probably been achieved. Some 40 minutes later, Woomera in Australia reported visual sighting of the sphere with its photo tracking camera.
Satellite beacon coming up. Still coming up. Begin search pattern A.
In on optics.
I have the satellite. Here she is.
1 hour and 50 minutes after launching, JPL picked up the echo signals and began tracking the satellite visually.
Hello, Bill. Yeah, we've acquired the satellite and we're tracking it with our radar.
And a few minutes later, BTL was in contact with the satellite.
The angle tracking looks smooth on the television
The
monitor.
experiment was a resounding success, and for the first time, a communications link had been established between two distant points on Earth using a man-made satellite. The practical implications of this success were enormous, for it meant that we had found a relatively simple and economical method of relieving our overcrowded communications lines and making the dream of global telephone and television communication a reality. Later tests proved that such satellites could also be used for teletype, facsimile, or even mail transmission. Today, in addition to developing larger and more rigid passive satellites similar to Echo 1, we are experimenting with active repeater satellites, which will be able to receive messages, amplify, and retransmit them. One communications company is so impressed with the commercial possibilities of this kind of communication that it has already begun to build its own experimental satellite system. We've also been very successful in using satellites to gather weather information. Since early 1960, we've launched 5 Tyros weather satellites. All of these satellites carried television cameras, picture storage tapes, and readout equipment, and electronic equipment to transmit the pictures to ground stations on command. Tyros 2 and 3 also carried infrared radiation equipment to measure the heat balance around the Earth. Orbiting about 400 miles above the Earth's surface, these satellites have been able to take pictures of the cloud cover over large areas of the Earth. They've sent back thousands of photographs, and with these, we've been able to reconstruct a weather picture of our country and a large part of the world. The success of our Tyros experiments has graphically demonstrated the great value of using satellites to study the mechanics of weather and improve our forecasting. For example, Tyros 3 located and televised pictures of 7 of the 8 hurricanes that struck the Atlantic coast during the 1961 season. It located Hurricane Esther 2 days before our weathercraft spotted the storm. But in addition to saving lives and reducing storm damage by supplying early warnings, this kind of advanced weather information also helps farmers select the best time for their planting and harvesting. And it may one day play an important role in helping us conserve our vital natural resources, such as land, water, and timber. But important as they are, achievements such as Echo and Tyros only show part of the practical side of our space exploration. For behind them are the important developments and discoveries that made them possible. And often, these developments and discoveries have a great practical value of their own, apart from their contribution to our work in space. The solar cells, which cover most of our spacecraft and convert sunlight into energy to supply power for their equipment, are a good example of one of these developments. Already, these cells are being used to furnish auxiliary power for communications lines, and they promise to have many other uses, such as a cheap and practical method of obtaining water to transform some of the desert regions of the world into productive land. Solar cells are products of solid-state physics, a relatively new area of science which has received most of its impetus from our space work. By producing revolutionary new semiconductors such as transistors, this remarkable new science has helped make micro-miniaturization possible, and in just a few years has transformed the electronics industry and created a multi-million-dollar industry of its own. And from these and related industries have come the fantastic data processing and computer equipment that we have today. Equipment which has become indispensable in almost every field of scientific research and business. These amazing machines make it possible to handle data and perform calculations in seconds, which only a few years ago would have required months or even years to do. NASA's Goddard Space Flight Center at Greenbelt, Maryland, uses batteries of these machines to monitor and guide our space flights. This center is also the heart of the International Ground Communications Network, which tracks and directs the Earth-orbiting manned flights of Project Mercury. Project Mercury represents our first venture into manned spaceflight, and it gave us an opportunity to work on the many basic problems that had to be solved before we could safely send men into space. Problems such as determining man's capability in the space environment, studying the conditions he would encounter entering and leaving space, and selecting and training men to work under these conditions, designing and building spacecraft that would safely carry men into space and back to Earth again, and developing boosters that would be capable of lifting such craft into space. It took us over 2 years to solve some of these problems, and in May of 1961, we were ready to test our solutions by sending a man into space. Alan Shepard was the astronaut on this critical test flight. This historic flight lasted only 15 minutes, but it proved that we could send a man into space and bring him back safely. And it also provided us with valuable information for our future space flights. Two months later, we sent a second man into space on a similar flight. This time, Virgil Grissom was the astronaut. Both of these suborbital flights prepared the way for the longer and more demanding Earth-orbiting flights, which were the primary objective of the Mercury project. In February of 1962, the stage was set for the first of these flights. John Glenn was the astronaut. Spacecraft and vehicle systems had been carefully checked and rechecked, and everything was working. This was the moment.
Motor systems. Retract now. Range operations. Roger. Mercury capsule. No. All pre-start.
And the attention of the entire world was focused on this flight.
6, 5, 4, 3, 2, 1, 0.
Roger, the clock is operating. We're underway.
You're loud and clear.
Roger, we're programming and roll okay. A little bumpy along about here.
Stand by
Roger. 2, 1, mark. Roger, backup clock is started.
The huge Atlas performed perfectly.
Seco. Plasma grades fired, okay.
A few minutes after liftoff, the rocket was separated and the spacecraft entered its programmed orbit.
Fine. Capsule is turning around. Oh, that view is tremendous. Roger, turnaround has started. Roger, capsule turning around, and I could see the booster during turnaround just a couple of 100 yards behind me. It was beautiful. Roger, 7. You have a go. At least 7 orbits. Roger, understand go for at least 7 orbits.
Over Africa, Glenn began to test his reactions to the eerie world of space.
Roger, this is Friendship 7. I can see the dark side coming up in the periscope back behind me at present time.
Soaring over the Indian Ocean, Glenn experienced his first nightfall in space.
The way the horizon looks is a very orange band just as the sun goes down. It extends way off either side, probably 45 degrees each side of the sun. Comes up into a lighter yellow, then a very deep blue, then a very light blue on up to the black of the sky.
Later, as he crossed the Pacific on his second orbit, he discovered his gyroscopes were wandering, and here again he was able to overcome the trouble by manual control. The fact that he was able to correct these dramatically points up one of the big advantages of manned spaceflight.
Coming off automatic in yaw, and yawing a little bit to the left to observe it. The flying with yaw handle pulled. Controlling on manual yaw. Once again, I can see lightning flashes under me very clearly.
As the third orbit about the Earth is completed, the retro rockets fire, slowing down the spacecraft, and it begins its fiery descent through the Earth's atmosphere.
Roger. Retros are firing. Yeah, baby. Are they ever? It feels like I'm going back toward Hawaii. Don't do that. You want to go East Coast. Main chute is on green. Chute is out in reef condition at 10,800 feet and beautiful chute. Chute looks good. On O2 emergency and the chute looks very good. Roger, what is your estimate on recovery time, over? Estimate pickup now at 20 minutes, over. Roger, understand 20 minutes to pickup. Landing bag is on green.
4 hours and 56 minutes after liftoff, after circling the Earth 3 times, the Mercury spacecraft landed in the Atlantic recovery area. This was not the first time a man had orbited the Earth, but it was the first time such a flight had been made openly, and the entire world shared in the triumph of John Glenn and the dedicated team that had made this flight possible. And apart from the enormous prestige and experience that our country had gained from this flight and from the flight of astronaut Carpenter, the entire world would also share in the benefits. For the volumes of technical information we had collected on these flights and the earlier ones would be made available to all scientists. The fact that a good deal of this was medical information measuring the physiological reactions and responses of the astronaut during the flight showed the important role that the life sciences were playing in this project. And it is in this area, which offers a vast new field of research for medicine and the other biological sciences, that our manned spaceflight promises its greatest practical benefits. In searching for ways to protect men from the hostile environment of space, these sciences are developing a broader and better understanding of the origin and basic nature of life. This research will eventually result in longer and healthier lives for everyone. Already, hospitals have shown an interest in the delicate sensors that were developed to record the astronauts' reactions during the tests. These sensors would enable doctors and nurses to keep continuous watch on the condition of their patients without disturbing them or even going near them. There's no doubt that these and many other developments and discoveries constantly being made by the life sciences in their space work will eventually find important practical applications in our daily lives. The X-15 project, which is another side of our manned flight program, is also providing valuable information for the life sciences. The idea behind this project was to develop a highly advanced aircraft that would combine and put to a test all our knowledge and skills in aerodynamics. The X-15 was designed to explore the flight problems encountered at very high speeds and at extremely high altitudes. It has been phenomenally successful in both of these areas.
3 minutes to drop.
Going to jettison. 0 jettisoning.
The design and performance goals were for a speed of about 4,000 miles per hour at an altitude of 50 miles.
Little launch light on. Launch light on, master arming. Okay, Scotty, you ready?
I'm ready when you are, buddy.
Okay, here we go with the countdown.
The great value of the X-15 is that it has served as a testing ground for many of our ideas in flight, and the technical information is sure to have a great influence on future design of our commercial aircraft. It has also proved that aircraft with certain modifications can operate well above the area of aerodynamic lift and at speeds many times that of our present aircraft. One of the most intriguing areas in our space exploration program is our plan to explore the moon and the planets in our solar system, and we've already begun to make the necessary preparations. Our first objective is the moon. The Ranger, which is designed to land an instrument package on the moon, is being used for our first explorations. It weighs about 750 pounds and is actually made up of 2 spacecraft. The main spacecraft, in addition to power, telemetry, and guidance and control equipment, will carry a television system to send back photographs of the moon's surface as it moves down on it. The second spacecraft, which will be ejected and actually land on the moon, will carry instruments to record lunar conditions and radio this data back to the Earth. Surveyor is another unmanned spacecraft that we shall use for lunar exploration. This spacecraft is designed for a soft landing on the moon, and it carries more delicate and elaborate instruments than the Ranger. Once the Surveyor lands, television cameras will begin scanning the surrounding terrain and examining the surface near the spacecraft, much the same way a man would if he were there. One of the cameras will even provide microscopic photos of the moon's surface directly under the spacecraft. After the television cameras have completed their survey, other instruments will go into operation. Instruments suspended on telescopic booms will record data away from the spacecraft. Even the lunar atmosphere will be analyzed. Drills will bore into the moon's surface and collect samples down to a depth of about 5 feet. The Surveyor carries its own laboratory to analyze these samples and transmit the results back to Earth. And since all these instruments can be separately controlled from Earth, any observation or analysis can be repeated if necessary. The Surveyor will function for anywhere from 1 to 3 months, and in that time we should be able to collect more information about the moon than man has gathered during the last 3,000 years. And this is the information we need to prepare for sending men to explore the moon. We have already begun building the huge vehicles that will be used for Project Apollo, our manned lunar exploration program. The primary objectives of this program are to send a crew of 3 astronauts to the vicinity of the moon and later land them on the moon and bring them back. The Saturn Booster will be used for the first Apollo flights. Saturn is capable of carrying many tons into orbit around the Earth or to the moon and even beyond. It will soon be ready for use. It is the first heavy rocket we've built designed specifically for space exploration. The booster, or first stage of this vehicle, is made up of a cluster of 8 large rocket engines capable of delivering 1.5 million pounds of thrust, which is equivalent to about 32 million horsepower. Because it's too large to be moved by rail or highway, the Saturn had to be shipped to its Cape Canaveral launching site by barge. The launch complex for this huge vehicle is the largest of its kind and covers some 45 acres. The big gantry or service tower that will hold the rocket as it is being checked out is 310 feet high. big Saturn booster has been successfully flight tested using dummy second and third stages filled with water to approximate their actual weight.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Ignition. All engines running. Gas commit. Launch commit. Liftoff.
At this early stage, it's impossible to evaluate the new knowledge and experience that we shall acquire through our lunar explorations. But if we're looking for immediate practical benefits, we can find them all around us. A good part of the country has already felt the impact of this program in the form of contracts, salaries, and the general increase in business activity that they produce. And this is generally true of all our space exploration, for the vast sums we are spending are being spent right here on Earth and right here in our own country. Most of the money that we are spending for space exploration is being channeled through the various NASA installations and research centers throughout the country. Through them into the thousands of factories, plants, workshops, schools, and laboratories, eventually ending up in the pay envelopes of many individuals across the nation. When we add up all this, and when we consider the many practical benefits we have already gained, and the many more we can expect, it would seem the big question today should be not why are we exploring space, but how could we have ever believed that we could ignore this vast, limitless area with all its promises?
One very interesting part of that film to me was the development of the mighty Saturn rocket, an enormous precision machine. Some early Saturn testing was done at Lewis Research Center in Cleveland. A scale model of the Saturn was evaluated in the supersonic wind tunnel to study heating problems that might occur during launch. These and other efforts in many parts of our country were preparing man to land on the moon. During our next episode, we'll see the first American spacewalk. Until then, this is Jim Burnett saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.